Hello everyone. So, welcome back again to the course on architectural design of ICs. So, in the last class we have seen that array multiplication architecture. So, why we use array multiplication? Because it has or it gives you that means regular structure for implementing any multiplication operation in compared to the tree based multiplier architecture. But it has the disadvantage of that means that means it has to, as the carry is rippled. So, that means the delay, or that means this particular array based multiplier architecture, they are slow in operation. Okay. So, and apart from that we have seen that Baugh-Wooley multiplier can be, that means for unsigned multiplication we have seen that that array multiplication architecture. So, that signed multiplication architecture or which is nothing but that Baugh-Wooley multiplier. So, is that means that signed multiplication architecture, that also can be represented in terms of array multiplier architecture. So, that we are to that means we will see it in today's class. Okay. So, if we see that this is the Baugh-Wooley 2's complement multiplier, that means all the multiples which I have to consider in Baugh-Wooley 2's complement multiplier system. Okay. So, as this particular operations are different in corresponds to that unsigned multiplier architecture. So, then if I have to, that means if I in unsigned multiplication, what was happening? So, this basically this operation, they are very much common. Okay. So, that means whenever I am adding at that time the corresponding this a2 x0 or a1 x1 or a0 x2, that I have already, that means added. Okay. So, but here you see some of these multiples, they are a4 x0 bar. Okay. So, here like a1 bar x4 and a4 and x4, here I have to add, that means these are the extra terms which are coming at this particular position. So, this addition of this extra overhead because of this 2, that means 2's complement multiplier, that we have to consider in this particular case. So, how we can do? So, in this array multiplier for this Baugh-Wooley multiplier. So, for that reason, so this was the initial array multiplier for this unsigned multiplication. Okay. But for what modification I need to make it this that means make it useful for Baugh-Wooley multiplier, that means I have to, because of this extra overhead or extra terms which are coming at this particular position. So, that means I need extra cells to be filled for implementing this array based Baugh-Wooley multiplier. So, what is that? That means at this particular, for this is P0, P1, P2, P3, P4 position, I am getting 2 extra terms which are A4 and X4. Okay. So, that means in initial that means multiplier, I am having only 4 stage here, but here I need another extra of this element, processing element, which will consider this A4 and X4 2, which will be added with the previous terms. Okay. And then that will produce the P4. Apart from that, what I need at the 2 to the power 8 position or this P8 position, what I need to add then again 2 extra terms which are A4 bar and X4 bar. Okay. So, that means at this particular position, here you see at this particular position, I need to add this A4 X4, A4 bar and X4 bar, which are coming through this, which is basically I need one extra processing element block which are of coming, that means which are taking the input of A4 bar and X4 bar. Okay. And then that is basically producing the P8 terms. Then again there is another extra overhead terms for this P9, that is 1. Okay. So, then that 1 again that will be added with the carry which is being generated from this P8 block. So, this carry is being basically the carry for this A4, X4, A4 bar and X4 bar, one carry, and the carry which are being forwarded from the previous stage, that which is that P6, sorry, for P7 stage. Okay. So, that carry also has to come to this P9 stage. Okay. So, then again that will be also pass that P7, P8 and then it will come to the P9 stage. Those carry also has to add and then I will get the final P9 over here. Okay. And then what other changes I have to do? The terms which are basically coming over here, they are different. So, initially it was not like A4 X0 bar, it was A4 X0, but here I have to put this as A4 X0. So, the same as A4 X1 bar, so instead it was A4 X1. So, those type of modification also I need to do to that means to make it 5 cross 5 array multiplier architecture for to complement Baugh-Wooley multiplier. So, here you see that shaded cell indicate additional cells for Baugh-Wooley multiplier. When sum logic is longer delay than carry logic, critical path goes through diagonal then along with the last row, and can reduce this by causing some signal to skip rows, and these are shown as curved arcs in figure. So, that means what I can do or that means what is basically happening over here, that means here what I am doing, I have increased the corresponding critical path over here. That means at that time it was 4 and then 4 here, but here now what it becomes 5 and then here also 5. So, that means now the corresponding critical path becomes to 10 full adder cell. So, initially it was what I said, if I use that means 5 cross 5 array. So, the total critical path delay will be m minus 1 plus m minus 1, that means 4 plus 4, that was 8 full adder cell. So, if you see that 4 over here and 4 over here. So, 8 full adder cell delay maximum, but here now it becomes 5 and 5, 10 full adder cell delay because of the extra modification which I need for this modified array multiplier architecture. Okay. And then this in this this corresponding the processing element block also will be changed. Initially what was there? Initially it was something like this sum and then carry and then x in, but here it is being ANDed, this x n is basically ANDed with a m. Okay. And then it is gone to the corresponding full adder cell and then it is producing S I and C I plus 1. Okay. So, this AND gate is basically included in the basic cell and then it gives this particular processing element are copied and it produces the corresponding this array multiplier. And if I just that means put this in a array multiplier architecture. So, that means in array based technique. So, at that time only this A4, A3, A2, A1 and X0, and in this particular this vertical direction and in horizontal direction I have to give this X0, X1, X2, X3, X4. Okay. And after that I will get the corresponding results P0, P1, P2, P3, P4, P5. That means here I do not have to put this initially what we are doing, that A0 and X1, that means A0 X0, A1 X0, A2 X0, all I am putting at this particular terms, but here I do not have to do that. So, only one x0, that means the ANDing operation has been done inside this processing element blocks. Okay. So, this is the unsigned multiplication architecture along with the modified processing blocks. So, modified processing block means initially we are considering only the full adder cell, but here we are considering the ANDing operation inside the processing block itself. Okay. Then suppose I want to, that means how can I improvise the corresponding speed of operation. So, what we know that for array multiplier architecture, this is the fixed, or the delay or the number of stage which I am getting for this the adder stage, they are fixed, which is of 8 number of full adder cell. Now, as that is fixed, now how can I, suppose I need to increase the corresponding frequency of that circuit. So, at that time how can I do? If I use pipeline technique, at that time I can improvise the speed of operation. So, how I can do that, that means the pipeline of this array architecture, how can I do? So, as you see, that means there is total 1, 2, 3, 4, 5, and in this case, so 5 stage of operation. So, in the vertical direction, what we give? We put this A0, A1, A2, that means all the A, all the multiplicand bit that we give. The multiplier bit are, that means applied in the horizontal direction. Now, this x0, that will be first ANDed, or that will come into the first set of this in the first row, okay, and that are with no delay element. In the next, this x1 will be delayed by 1 register, or it will be delayed by 1. Okay. So, then again that will come. Then x2, as it has been applied on the, or the partial products will be generated at the second level, that means third level. So, it has to pass to the 2 delay over here. So, the x2 has been applied after 2 delay. So, in the same manner x3 has to applied after 3 delay, and x4 has to applied at the after the 4 delay. So, that for each of these stage the delay element I have put. So, this is for the input side. Then what will happen for the output case? For the P0, for the P0 element, it has to pass through the number of delay element. So, actually if I just, that means, so whenever I will apply this A0 and X0, it will produce this P0 terms. But this for P9 case, how many, that means what is the number of that register block which I has to pass? That is basically 4 for this, because x4 has been applied after 4, and whenever I will get, that means this particular stage, okay, if I go back to this. So, at the very end, then again I need to pass through this like a carry propagate adder or ripple carry adder for generation of this P5, P6, P7, P8 and P9. So, this can be done based on, as this carry is basically propagating. So, initially this P4 signal, sorry P5 signal, that will come for producing the P6. Then whenever this P6 will be generated, then the corresponding output from this two particular block, they will be passed to, because that is one level next. So, that these two particular signal, they will be last and they will come after this. In this particular stage, these 2 will be come after 2 delay element and these 2 will come after 3 delay element. That means, so after 7 delay, 4 over here and 3 for this particular case, this P8 and P9 will be generated. But if I see this particular P0 term, so at the time P0 and X0 is basically generated at the 0th clock cycle. This P8 and P9 they has been generated on the after the 9th clock cycle, that means 4 and 3, so 7th clock cycle. But P0 X0 has been produced in the 0th clock cycle because there is no delay element over here. So, that means this P0 has to be delay. So, P8 P9 that has to be synchronized with P0. So, that means this has to also pass through this total 4 over here and 4 for this and 3 over here. So, after that means 8 delay element it has to pass. Why? Because at the 8 clock cycles only I will get this P8 and P9. As this particular cell is producing P0 at the 0th clock cycles, so that means this has to pass through 8 corresponding number of stage. Okay. So, P0 has to pass through this, then P1 has been produced at what? P1 has been produced at 1th clock cycle. So, that means it has to pass through 7th another delay element to be synchronized with P8 and P9. So, that is why if you see, so for P0 1, 2, 3, 4, 5, 6, 7, 8, 8 number of delay element it has to pass. So, after that P0 will be come over here. So, for P1 it has to pass through 7th because it is produced at 1 clock cycles. So, that means 1, 2, 3, 4, 5, 6, 7. Then P2 it has produced at 2 clocks, that means 2nd clock cycles. Okay. So, that it has to pass through 6. So, 1, 2, 3, 4, 5, 6. Then P3 that has to at the 3rd clock cycle it is produced. So, another 5 clock cycle it has to pass. So, 1, 2, 3, 4, 5, 3, 1, 2, 3, 4, 5, 5 for P3. Then 4 has to, that means produced at 4th clock cycle. So, 4 another it has to pass. So, that means P4 which is passing through 1, 2, 3, 4, 5. Okay. So, then for P, what will happen for P5? P5 is the 5th. After 5th clock cycle it will produced. So, 5th clock cycle produced means it has to pass through another 3 extra registers. So, 1, 2, 3. Okay. So, then again P6 is produced after 6th. So, that means now 6th is basically, then again it has to pass to another 2. For P7 it is at 7. So, that means it has to pass through another 1. P8 and P9 that has produced at 8 clock cycles. So, this has to pass through no other delay element. So, that means whenever I am getting at the 8th clock cycle I will get this P0 to P9. So, why 8 clock cycles I need or 8 number of registers I need? Because 8 number of full adder cell I am doing or adding in this particular array multiplier architecture. So, this is the structure for pipelined 5 cross 5 multiplier. Okay. So, now here what is the corresponding delay for this particular case? Okay. So, now the delay for this particular case will be of how, that means what will be the corresponding delay element over here, because the inputs are also passing after one delay element. That means, here whenever this will be nothing but one this processing element blocks delay. Why so? Because not this one. Okay. Here only this 4 that processing element, sorry, 5 total processing element block. So, that will be the corresponding delay over here, because at the final level I have to process this through 4 and one full adder cell delay for this particular each of this block over here. Okay. So, 5 for the final and 1 for the corresponding delay for this particular cell. So, total 5 I have to, because the carry is basically propagating in this particular direction, right. So, that means total 5 delay element, full adder cell delay element will be the delay for this pipeline 5 cross 5 multiplier architecture. Okay. So, this is the pipeline structure of 5 cross 5 array multiplier architecture. So, then again that means till now we are discussing about this multiplication, where this multiplier and multiplicand bit, that means the numbers, they are different. Then squaring, I think squaring means what? X square or y square or a square or b square means what? I am multiplying the same number, that means where the multiplier and multiplicand bit or the numbers are same. So, at that time that is the square. So, if I multiply a with b, at that time it will be a b. Otherwise, if I am multiplying a with a, so at that time it will be a square. Okay. Suppose these two multiplier and multiplicand bit, they are same. So, at that time in regular multiplier architecture, if I put that, so at that time that circuit also will give you the same results. But if I need one squaring circuit, at the time as there is two the number of multiplier and multiplicand are same, at the time can I produce one optimized circuit for that, for this squaring operation? If I can, then how I can do that? Okay. So, what are the changes will be there, or what will be the idea for doing the optimization whenever we will draw or we will come to the architecture of squaring circuit, that we will see now. Okay. So, in general, if I that means want to multiply x with x, where each of are like 5 bit. So, in this position this will be x 0 x 0, this will be x 0 x 1, and again for this particular case it will be x 0 x 1. So, x 0 x 0 means what? X 0 is multiplied with x 0 means what? This is nothing but x 0. If I am multiplying a with a, means that is a. Why is so? Because if you see, if I am multiplying a with a, that is a, because if a value is 0, so 0 into 0 means 0 and 1 into 1 means 1. So, whatever is the value of a, that I am getting at the output. So, that is why a dot a means that is nothing but a. So, x 0 dot x 0, that will be nothing but my x 0. Okay. So, then for this particular, for P 1, it will be this and this. So, x 0 x 1 and x 1 x 0. So, that is nothing but this x 0 x 1 and x 0 x 1. So, if I that means add a plus a, so it will be twice of a. So, twice of a means what? The a will come to the next MSB position. So, that means this position, now this x 1 x 0, that will come to the corresponding next. So, this will move to the next column. So, now for P 2, what will be the case? For P 2, it will be x 0 x 2 or x 2 x 0, then it will be x 1 x 1, then it will be x 0 into x 2. Okay. So, for P 3 case, what will be the case? That means for one it is this, for another one this, and for another one this. So, x0 x2, x1 x1 and x2 x0. Okay. So, this and this is same. So, this and this same means, so this will move to the next column, and x1 dot x1 means nothing but x1. So, this x1 x0 has come to this and it will be added with x1. For this particular position, so now the thing will be that x3 x0. Okay. So, then x2 x1, then x1 x2, x0 x3. So, x3 x0 and x3 x0 are same values. Okay. So, then that will move to the next, and here you see x2 x1 and x1 x2, they are also same. So, then again that will also come to the next. So, that means at this P3 position what will be there? This x0 x2 only. So, x2 x0 is coming over here. So, in this manner, if I just do it for all this position, finally what we will get? We will get the partial product something like this: x1 x0 x1, x2 x0 at this particular place, x3 x0, x2 x1, x2, something like this I will get. Okay. So, then again can I, that means optimize this more? So, if I add this x2 along with x2 x1, if I add, so at the time it will be x2 1 plus x1. So, what is this value? 1 plus x1, that is nothing but 1. So, this is x2. So, that means only x3 value I have to add this particular things. So, the same thing will happen here for x3 x2 plus x3, that will be nothing but my x3. So, again more reduction in this, that means multiples of this can be done. So, finally, what I will get? Finally, this can be okay. So, optimization can be done in this way, and finally, for this particular case I will get the terms over here 2, 2, 2 and 2, and then using any fast adder, if I just add, at the time I will get all these values of this. So, that means now if I am multiplying, that means for the squaring circuit it requires, or we have optimized because of this logical, that means because of this Boolean algebra or this logical optimization, we will get the circuit only considering very nominal number of the basic gates. Okay. So, that is the squaring circuit, that means the architecture of that squaring circuit. Now, I will come from this particular equations. Okay. So, this is the optimization while we will do the squaring circuit. Okay. And then using one lookup tables. What is lookup tables? Lookup tables is nothing but your like a, that means some values which are stored in memory. Okay. So, this is nothing but like a ROM structure. So, in ROM what we do? We only put the values and read by giving the proper address. Okay. So, in squaring what we know, because for 0 it will be 0, for 1 it will be 1, for 2 it will be 4, for 3 it will be 9, for 4 it will be 16. So, we know as the values are same. So, we know what will be for 1, 2, 3, 4, 5, 6 something like this, what will be the corresponding squaring value. So, if I just store it in ROM and then this input, that if I just, that means give as an address to that ROM. So, that means obviously I will get the corresponding output very easily. Okay. So, this circuit will be very much optimized. So, that means I do not have to use any extra logic gates or logical terms to produce the corresponding squaring of the numbers. But This is advantageous when the number of, that means the length of input that I am considering lesser, because for 4 bit there will be 16 number I will get. So, that means in the ROM table the depth of ROM will be 16. If I consider this A of 10 bit, so at that time what will be the number of combination over here? So, that will be 1024. So, at that time it will, that means produce this, that means it will require the depth of this ROM, that means depth of this ROM, that is 1024. Not only this 1024 depth, it will increase this width of this too. Okay. So, that means 1024 number along with the corresponding depth, that means that is of 20 bit for each of this storing this particular that means this one particular ROM bit. So, I require 20 bit. Okay. So, that means total 1024 into 20. So, that will be the size of this ROM. So, at that time it will consume more power and it will be slow in operation in compared to if we implement those squaring circuit using logic gates. So, at that time this lookup table based squaring circuit is not that much efficient way to implement it. So, for the lower number of values or the lower width we consider for A, at that time it is advantageous this lookup table based, otherwise this structure is not that much advantageous in terms of power or in terms of speed or in terms of area. Okay. So, this is the, that means another squaring technique or squaring architecture for how we can implement or how we can do, and at the very, that means what I suggest that it is whatever we are discussing here, that is not the end. People are basically day by day they are working or they are doing research on this different architecture, finding out different architecture for high performance multiplier architecture. Okay. So, more if you are interested on more on this learning on this particular multiplier architecture, please follow any scientific websites like IEEE or Google Scholar. Okay. So, any of this and use your that means, and from that particular point you come down how you can, that means you note down what are the problems or why that or how you can improvise the corresponding circuit, and then you try to build your own multiplier architecture for your particular application. Okay. So, this is that means the end for integer multiplication. Okay. So, now in the next we will see this suppose in some of the case I need to multiply floating point number. So, at that time how can I do, though we are in the fixed point domain. So, how can I do this floating point number multiplication? Okay. And what are the, that means way or way of optimization, or is there any way of optimization that we can do whenever we will consider this. So, that we will see from the next class onwards. Okay. So, this is it. Thank you for today's